Welcome to this lecture on the principle of immunology. Today, we are diving into a fascinating and foundational topic, antigens and immunogens. If you have ever wondered how vaccines work or why some molecules trigger massive allergic reactions while others are completely ignored by our bodies, you are in the right place. Let us build your understanding from the ground up. To begin our journey, we must understand the core distinction between two terms that are often confused. Imagine a highly secure building. An antigen is like someone wearing a readable name tag. The security guards recognize them, but they do not necessarily sound the alarm. An immunogen, however, is someone who not only gets recognized, but causes the guards to hit the panic button, launching a full defensive response. The golden rule here is that all immunogens are antigens because they must be recognized, but not all antigens are immunogens. This difference is the absolute foundation of vaccine development. Now that we understand what an antigen is conceptually, let us look at how it interacts with the immune system chemically. When an antigen bumps into an antibody, they bind together. We measure the exact strength of this grip using the affinity constant, denoted as K sub A. Conceptually, this formula calculates the ratio of successfully bound pairs to the free-floating molecules that failed to bind. In the equation, the numerator represents the concentration of bound antigen-antibody complexes. The denominator represents the free antigens multiplied by the free antibodies. When the concentration of bound complexes increases, the affinity constant increases, meaning a much stronger physical grip. Before we move on, let us see this formula in action with a concrete example. We are testing a newly discovered viral antigen. We are given that the concentration of the bound complex is 0.008 moles per liter. The free antigens and free antibodies are both at 0.002 moles per liter. We chose the affinity constant formula to find the exact binding strength. By plugging in our values, we multiply the denominator first, then divide the numerator. The final answer is 2,000 liters per mole. This relatively high number tells us the immune system has a solid physical grip on the virus. This formula we just used leads us to an important question. How do we mathematically prove which antigen is superior? Let us set up a comparison between antigen X and antigen Y. For antigen X, we are given a bound complex concentration of 0.010 and free components of 0.005. We plug these specific equilibrium concentrations into our affinity formula. By squaring the free components in the denominator and dividing, we establish a baseline affinity constant of 400 liters per mole. This chunk of our derivation sets the benchmark we need to evaluate the second antigen. Continuing our derivation, let us look at antigen Y to find our final result. Antigen Y has the same bound complex concentration, but far fewer free molecules left in the solution at just 0.001. When we run these smaller numbers through the denominator of our formula, the math yields a massive affinity constant of 10,000 liters per mole. Because 10,000 is significantly greater than 400, we have mathematically proven that antigen Y binds much more tightly. The intuition here is simple. Fewer free molecules mean a stronger, more stable connection, making antigen Y a far superior target for immune recognition. Having proven how binding strength works, let us visualize these categories. Look at this diagram showing concentric circles. The large outer circle represents all antigens, which are any molecules the immune system can bind to. Inside it, the smaller circle represents immunogens, the special subset that actually triggers a response. Notice the small dots labeled haptens. They sit inside the antigen circle but outside the immunogen circle, meaning they are recognized but too small to trigger an alarm on their own. This visual perfectly summarizes the golden rule we discussed earlier. This visual distinction brings us to our next major concept. What exactly makes a molecule an immunogen? The immune system does not react to everything. A molecule must possess extreme traits to force an attack. First is foreignness. It must look biologically different from your own tissues. Second is molecular size. Large molecules, over 100,000 Daltons, are potent, while tiny ones are ignored. Third is chemical complexity. A diverse protein is highly immunogenic. Finally, it must be susceptible to processing, meaning immune cells can degrade and present it. These 4 factors dictate whether a molecule is a silent antigen or a powerful immunogen. Knowing these factors allows us to manipulate the immune system, which introduces us to haptens and adjuvants. As we saw in the diagram, haptens are tiny chemicals, like penicillin, that are completely invisible to the immune system on their own because they lack size and complexity. They only become dangerous immunogens if they accidentally attach to a larger carrier protein in your body. On the flip side, when scientists design safe vaccines, the viral pieces are often too small to work, so they add special substances called adjuvants. Adjuvants artificially increase the size, complexity, and foreignness of the vaccine, tricking the body into launching a massive, life-saving response. Now that we understand how size and complexity matter, let us look at the mathematics of large molecules. Real immunogens are huge structures with many spots for antibodies to grab simultaneously. We measure this combined overall gripping strength using the concept of avidity, denoted by capital A. Conceptually, this formula shows that total strength is not just added up, it grows exponentially. Capital A is the total avidity, Ka is the intrinsic affinity of a single binding site, which we calculated earlier. The exponent n is the valency, meaning the total number of binding sites. When valency increases, the total avidity explodes upward. Let us apply this avidity formula to see exactly how a single binding site behaves. We're looking at a small, simple antigen with only one binding site, meaning its valency, n, is exactly 1. We are given a baseline affinity constant of 10 to the power of 4. We chose the avidity formula to find its overall functional strength. We plug in 10 to the power of 4 and raise it to the power of 1. Mathematically, any number raised to the power of 1 remains unchanged. The final answer is 10,000. Physically, this represents a very weak, easily broken interaction with the immune system. Now that we have our baseline, let us prove mathematically why larger, complex molecules are better at engaging the immune system. We take a complex immunogen that has the exact same basic binding structure, meaning its intrinsic affinity is still 10 to the power of 4. However, because it is larger, it has 3 binding sites, giving it a valency of 3. When we substitute these values into our avidity formula, the mathematics dictate that the binding strength is raised to the 3rd power. This step is crucial because it shows that multiple bonds do not just add together, they multiply each other's stability. Let us finalize this derivation and compare the results. By calculating 10 to the 4th power raised to the 3rd power, we get 10 to the power of 12. When we compare this to our simple antigen score of 10,000, the difference is staggering. The complex immunogen is 100 million times stronger. The intuition here is that multiple bonds stabilize each other, making it exponentially harder for the molecule to break free. We have just mathematically proven exactly why large, complex molecules with high valency are highly successful immunogens that trigger unstoppable immune responses. This exponential growth leads us to a real-world clinical application, calculating the effect of adjuvants. We are given a raw vaccine protein with an affinity of 10 to the power of 3 and a base valency of 2. We need to find the avidity before an adjuvant is added. We use our exponential formula, plugging in 10 to the power of 3 squared. The final answer is 10 to the power of 6, or 1 million. While 1 million sounds large, in the biological world, this unenhanced state might not be enough to trigger a strong, lasting immune response to protect the patient. To see how we fix this weak vaccine, let us derive the impact of adding an alum adjuvant. The adjuvant physically clumps the proteins together, creating a much larger structure. This effectively increases the valency from 2 up to 5. The baseline affinity remains 10 to the power of 3. When we plug this new valency into our formula, we raise 10 to the power of 3 to the 5th power. This mathematical step represents the molecular explosion in binding strength. The result is 10 to the power of 15, a staggering 1 quadrillion. To conclude this derivation, we must find the exact factor of improvement caused by the adjuvant, which we will call multiplier M. We divide the new, enhanced avidity of 10 to the power of 15 by the old baseline avidity of 10 to the power of 6. By applying the rules of exponents, we simply subtract 6 from 15, leaving us with 10 to the power of 9. This proves that the adjuvant increased the vaccine's binding strength by 1 billion times. Physically, this means the immune system is 1 billion times more likely to capture and react to the vaccine, saving the patient's life. To truly cement this concept, let us look at this schematic diagram comparing valency and avidity. On the left, you see a single binding scenario. A Y-shaped antibody is grabbing a small green antigen at just one site. As the label says, this is a weak association. Now follow the arrow to the right. Here we see a large bacterial cell. Because it is large and complex, multiple antibodies are binding to it simultaneously. This is a multivalent scenario. The labels clearly show that these multiple bonds create tight binding, resulting in high avidity and a strong immunogen. This perfectly illustrates the math we just calculated. We have covered a lot of ground today, so let us review our key takeaways. First, remember the golden rule. All immunogens are antigens, but not all antigens are immunogens. Second, we learned that affinity measures the strength of a single bond, while avidity shows how multiple bonds exponentially increase total gripping strength. Finally, factors like size and complexity are essential, which is why we use adjuvants to transform weak antigens into powerful, life-saving vaccines. You now have a deep mathematical understanding of how the immune system recognizes threats. Great job!